Welcome to Healthy Living, Healthy Planet Radio, sponsored by EarthX, the world's largest environmental experience, and also sponsored by Natural Awakenings magazine. Live your healthiest life on a healthier planet. Now here's your host, Bernice Butler.
Welcome to Healthy Living, Healthy Planet Radio today. We are now at the beginning of our fourth season, and we are more excited than ever to continue to help you explore and understand that unbreakable relationship between your health and the health of the planet. Here, we look at the hottest topics related to our environment and its sustainability and how they affect your health and wellness. Here, issues like climate change, plastic pollution, extreme weather events, and others will meet up with everyday impacts like allergies and asthma, digestive issues and gut health, cancers, lung and heart issues, and more. So listen in today as we interview experts for today's show in our series on extreme weather events. And today we're going to be talking about hurricanes, tornadoes, storms, and floods. Now, extreme weather continues to swell like our U.S. coastlines do during high tide. And with it comes a realization that climate changes we were warned about many years ago, that they're already here with us today. For decades, the core question in the public debate over global warming was, will all these scientific projections and things they're talking about really come true? Now, Britain has its hottest summer ever, and New Zealand its third warmest winter in a row. The Rhine River, the Danube, the Yangtze, and the Colorado rivers all have dried out at some point, thus interrupting commerce and power generation, and heat records are being smashed every year. Weeks of catastrophic flooding submerged almost a third of the country of Pakistan, killing more than 1,700 people and destroying about 1.3 million homes. And scientists say that flood infrastructure, public awareness campaigns, and satellite or drone monitoring may all be part of improved disaster management once the country can think about such things again. If nothing else, Americans who popularized climate change denial are now beginning to believe their own eyes. Almost half of Americans now report they've seen global warming affect other people, and 30% say they've experienced its effects personally. Research also shows that Americans believe most of their compatriots don't support climate change policies when actually the opposite is true. And that implies regular, ordinary Americans aren't nearly as split over the need to take action as some politicians might want to believe. Nevertheless, the big picture metrics suggest there's still an enormous amount of work to do if we're going to avert the worst of the projections that we've heard. It's sometimes said that climate change will cost rich countries like the U.S. money, and it'll cost poor country lives. And I think we're seeing some of that. The science says we'll all pay, however. That's the bottom line. Heat alone is the leading cause of weather-related deaths in the U.S., and it's such a problem globally that the cardiology profession might actually need a specialty in climate change and cardiovascular disease. Then there's floods. The floods in Texas a few years back and in other parts of the southern United States after Hurricane Harvey and other hurricanes have garnered international attention. And at the same time, floods in India, Nepal, Bangladesh, and again, Pakistan have killed thousands of persons and significantly affected tens of millions. Floods are the most common natural disaster occurring worldwide. And in 2016, floods, excluding landslides, affected more than 74 million persons globally and resulted in almost 5,000 deaths and had an economic impact of greater than $57 billion. Of the 161 significant flood disasters worldwide in 2016, 43% occurred in Asia, 23% in the Americas, and 12% in Europe. Now, floodwaters pose immediate dangers to human health, but also long-term effects resulting from displacement, from worsened living conditions, with the risk of infection after exposure to floodwaters, capturing considerable public attention and is a common cause of presentation for healthcare after the flood events. The impact of flood disasters is expected to grow in the future, owing to the effects of climate change and to the effects of population shifts. For example, in China, the number of elderly persons living in what they call rainstorm hazard areas increased by 38 million between 1990 and 2010, and I'm sure it's more now. And this greatly increased the complexity of planning for future flood disasters. Extreme weather events increase the risk of illness through, as we mentioned earlier, increasing temperatures and heat, more frequent heavy rains and runoff, and the effect of storms. Health impacts may include things such as gastrointestinal illnesses like diarrhea, and effects on the body's nervous and respiratory systems or liver and kidney damage. Extreme weather events are expected to continue to become more and more frequent as a result of climate change. Climate extremes can have devastating effects on human societies. History, in fact, records widespread disasters, famines, and disease outbreaks that have been triggered in our past history by droughts and floods. Now, these complex, large-scale disruptions used to exert their worst effects in poor countries, but now even the richest industrialized nations and societies are not immune. Extreme weather events are, by definition, rare events. And many are more complex, event-driven extremes, such as droughts, floods, or hurricanes. And these do not necessarily occur every year at a given location, but now we see they are occurring somewhere almost all of the time. And all of these have significant impacts and consequences on our health, such that it's not an option that we have to care about them and know about them. Now, the benefits of protecting our climate aren't only financial, though. It turns out that the same ecosystems that bring us water, food, flood protection, and biodiversity also bring us happiness. And a review of many dozens of previous studies identified 227 ways that nature affects people's well-being. And again, nature is at the front line of these extreme weather events. Now, this is a lot, but here today to help us explore and unpack some of this are some experts that we're looking forward to talking with. We have with us John Nielsen-Gammon, and he is a Regents Professor at Texas A&M University. He is Director of the Southern Regional Climate Center, and he is a Texas State climatologist. John is in the midst of a 2-year term as President of the American Association of State Climatologists, and he was named a Fellow of the American Meteorological Society in 2011. John conducts research on a large-scale and local-scale weather, climate, and air pollution with a focus on intense rainfall and droughts. Welcome, John. Did I get all of that right?
Yeah, thank you. Appreciate it. Good to be with you.
And our other guest is Justin Mankin. And Justin Mankin is a climate scientist appointed as an assistant professor in the Department of Geography at Dartmouth College and at the Dartmouth Climate Modeling and Impacts Group. He also holds appointments at the Department of Earth Sciences and the Ecology, Evolution, Environment, and Society graduate program. He is also an adjunct associate research scientist in the Division of Ocean and Climate Physics at Lamont Doherty Earth Observatory of Columbia University. Welcome, Justin. And did I get all of that right?
Yeah, great. Thanks, Bernice.
And we are very grateful, Justin, that you could join us here at the last minute. And we're going to go to break shortly. But before that, I want to start out with John, because I know you have to leave us. So, John, most of us feel that we are seeing and experiencing more extreme weather and some of the most extreme weather of our lifetimes of all types. Can you tell us if this is true, or are we just feeling like that?
Well, we are getting more extreme weather in general. Some of it is expected from climate change, and some of it is we hear about it more because we're a lot more connected globally. There's also a couple types of extreme that are getting better, like extreme cold is not as cold as it used to be, and there are a few things we'll talk about which we can't really tell, but there's a lot of things pointing toward getting worse.
Indeed. And it's kind of like, well, it looks like the extreme cold is lessening.
That's right. As temperatures are shifting, we're getting more hot records and fewer cold records.
That's global warming. We're going to go to break right now. We'll be right back on the other side and let John Nielsen-Gammon continue to tell us about this. We've been with and are with John Nielsen-Gammon with Texas A&M and Justin Mankin at Dartmouth. Thank you all. We want to give a shout out now to our sponsors. That is Natural Awakenings, Dallas-Fort Worth Metroplex Magazine, the Green, Healthy, and Sustainable Living Authority for the DFW Metroplex and North Texas communities. Print issues of Natural Awakenings can be found in most Whole Food markets, natural grocers, central markets, sunflower shops, and many, many other locations, as well as available free for download online at nadallas.com. Check them out. Our other sponsors are North Haven Gardens, serving the Metroplex since 1951, the most respected horticultural establishment in North Texas, offering gardening and plant education, concierge services, DIY classes, gifts, and more. Check them out at nhg.com. And their other sponsor is Lynn Dental Care, practicing dentistry for over 38 years with a holistic approach, looking at the whole body. Specializing in periodontics, Dr. Lynn is board certified by the International Academy of Oral Medicine and Toxicology. Check them out at lindentalcare.com. Thank you, sponsors. Welcome back to Healthy Living, Healthy Planet Radio, to today's show on extreme weather events, focusing in on hurricanes, tornadoes, storms, and floods. And we are back with Dr. John Nielsen-Gammon, our Texas State climatologist, and he's at Texas A&M, and with Justin Mankin at Dartmouth. And again, we're very glad that these two gentlemen could really clear their schedules somewhat to join us today. Now, before the break, we were talking with you, John, about bringing together the reality of the severity and the frequency of storms and weather events with our perception. And you have assured us that it's not just in our minds. It's true. So moving from there, though, John, focusing on rainfall for a while, can you connect the dots for our listeners about what causes it and what are the determinants of the amount of rainfall and where it falls? Sure.
Well, of course, to get rainfall, you need to have plenty of water in the atmosphere in the form of water vapor. If it rises and cools, you start getting clouds and you start getting rainfall. Climate change connection is in a couple aspects of that. One is the hotter the temperatures, the greater the amount of water vapor that the atmosphere can hold. And so when it rises and water condenses, you're getting more water condensing and you're getting more intense rainfall. The other aspect of it is that weather patterns can change also. You can get different structures of storms, you can get different frequencies of storms, they can follow different paths, and that will influence heavy rainfall as well. It could make it more frequent or less frequent. Texas specifically, we're getting more intense rainfall events, and it's that temperature effect that seems to be the dominant one here.
In other words, because you said that the hotter it is or the more heat, then it begins to draw up the precipitation or humidity into the air, which makes for the rainfall. So does that mean that when we have these extremely hot summers, then does that mean that we can look forward to or need to anticipate heavier rainfall, more rainfall incidents, or what?
Well, when we get a hot summer, usually that's partly a side effect of the ground drying out. So it means we've actually gotten less rain than normal. The temperatures to keep track of are supposed to be the ones in the Gulf of Mexico because that's where the evaporation is happening, and that's where the moisture is that's feeding us. And so actually when you've got Gulf of Mexico temperatures running well above normal, that could be a warning sign that we have an increased upper limit as to how intense the rainfall could get.
And that's Gulf of Mexico. What about on the Atlantic side? If it's hot there too, does that mean...
tropical Atlantic mainly. The air that feeds the precipitation in the East Coast, especially if it's during the summertime, is probably coming from the tropical, subtropical Atlantic, getting it in from the Gulf Stream, and then being carried onto land. So, yeah, the oceans are supplying most of our moisture, and then our rivers put moisture back.
So this is how you climatologists and scientists tell that we're going to have a pretty ferocious rainy season.
Yeah, well, you can't tell when you're going to get a specific extreme event because, by definition, extreme events are kind of rare.
Bypass definition. They're rare.
That's right. Well, it's sort of two definitions. One is like extreme means rare in the sense of, temperatures only happen once a century. In fact, they only happen once a century, although they could change over time. Other type of extreme events are extreme just by their nature. Things like tornadoes and hurricanes, they cause damage just by their existence, basically, as long as they're encountering something over land. And so wherever they happen, they're extreme. They tend to be rare, but we think of extreme because they're damaging. Temperatures are damaging because they're outside the realm of what we're used to. The temperatures we see in the Sahara Desert are relatively comfortable for people who live in the Sahara Desert, but they'd be pretty devastating if we experienced them.
I got you. So we need to refocus our definition, our working definition of extreme. Extreme is referring to the nature, the damage, the severity of the event, as opposed to the volume of these events, because they are no longer
it's a
rare.
little bit of both, really. Yeah.
I got you. Thank you. Justin, why are we seeing and hearing about so many more what I call freestanding storms and floodings?
Yeah, I mean, I think it's a fair question. It goes back to precisely the mechanisms that John was talking about, right? But that, we have a situation where just based on thermodynamics, right, like kind of the fact that we have a warmer atmosphere, it tells us pretty clearly that water fluxes are just going to increase from warming, which means that when it does rain, it's just going to rain heavier. And so a really clear expectation we have is that what was kind of a historical, thunderstorm or afternoon rain shower, that's just going to be a more intense storm. And, to the extent that warming consolidates rainfall, that also means that the periods between rain events could be prolonged, particularly for a place like Texas.
Another part of that issue is that we actually aren't seeing an increase in the number of hurricanes overall, at least not globally. But the hurricanes we do get are typically coming in with heavier amounts of precipitation. Harvey in 2017 was sort of the classic example of that. And the research that came out of that storm said that basically the intensity of rainfall was increased by about 15% because of climate change, even though the odds of a hurricane hadn't changed.
Yeah, and I think John's point, there's going to be differences from, ocean basin to ocean basin, depending on, how the sets of ingredients that favor hurricane development change in those different basins. A really bad thing for hurricane formation is wind shear, for example, which is just kind of vertical differences in wind speed at different altitudes in the atmosphere. And so high wind shear would be, winds of very different speeds or very different directions at different levels in the atmosphere. And a hurricane really kind of requires, very low wind shear conditions. Otherwise, it will tend to kind of break up the structure that allows a hurricane to intensify and kind of draw heat and moisture from the ocean surface and organize itself into a storm that can be sustained for several days. And so, a key question that a lot of hurricane scientists are working on is kind of how these different ingredients are going to change from ocean basin to ocean basin and what that means for changes not just in hurricane frequency, but also magnitude.
And when you say basin, you're talking maybe like the Atlantic, the Gulf, and the Pacific.
Precisely, yeah, the ocean basins themselves.
I'm gathering that each one of those has its own character. Each one of those is where the hurricane is going to start, and depending on what's going on in each of those places determines what we get.
Yeah, we might have a year with lots of activity in the tropical Atlantic, whereas the Eastern Pacific might be kind of quiet, and that's the sort of circumstance we thought we were going to see this year with La Nina conditions, but actually the forecasts have been a little bit more pessimistic than reality has been. We've managed to luck out, except for Florida for the most part. on this year's hurricane season.
Now, I've also heard, and I want to ask you about it, that, and we just have just a few more minutes to go before this segment closes, that there may be a cycle in which the hurricanes will go from the Atlantic to the Gulf to the Pacific. Is that been historical? Is it true, or is it going to remain true given the impacts of climate change?
Yeah, we've seen variations of hurricane tracks from decade to decade, and variations of hurricane frequency in the Atlantic from decade to decade. We've really had an active period starting since about 1995 compared to, say, the previous couple decades. But it turns out that it's an open question as to what's causing that. We used to think that basically you had the Atlantic Ocean switching from warm to cold and then warm again over multiple decade periods. But it turns out that there may also be a role for man in that, in the sense of air pollution and particulate matter may have actually blocked a lot of sunlight in the Atlantic during the 1970s and 1980s until we started cleaning up our act. And that probably played a role in suppressing hurricanes during the latter part of the 20th century. And now, in a sense, they're getting back to normal.
Indeed, and I know that you have to leave us shortly, John, and we're going to go to break here in a minute, too. But I do want to unpack a little bit more something that you mentioned, and that is basically how environmental degradation is also driving the extreme weather events.
Yeah, we think of it in terms of just the climate change and the temperatures, but rainfall in particular depends a lot on the sort of pollution that's in the atmosphere. If you have a very, very clean air, pollution can make precipitation more intense, and then it could get to a point where it becomes less intense again. And unfortunately, it's one of those things where you sort of have to make a trade-off of different effects, and the main effect that we worry about with pollution is the health impacts. And if reducing pollution has sort of knock-on effects to the climate, we sort of have to live with that because we have to live in the first place.
Indeed. We're going to go to break, and I know that you have to run, but right after the break, I want to talk about what the wildfires are doing to rain. We'll be right back on the other side with Dr. John Nielsen-Gammon, the Texas State climatologist, and with Dr. Justin Mankin at Dartmouth University. Thank you all. We'll be right back. Welcome back to Healthy Living, Healthy Planet Radio today, to our series on extreme weather events. And today we're looking at hurricanes, tornadoes, storms, and floods. And we are back with John Nielsen-Gammon at Texas A&M. He's our state climatologist, and Justin Mankin at Dartmouth. And again, thank you all for being with us. John, last thing before we know we have to let you go, and that is to talk to us just for a minute, because you said that the pollution is affecting our rainfall and our rain patterns. So what are all these wildfires in the western part of the United States and coming here to us in Texas, what are they doing? Because that's creating a great degree of particulate matter and air pollution. So what, connect the dots there?
Yeah, it does. It's sort of a combination of things again, because you've got, when we get our air from the high terrain of the western United States, it's been heated just in general because it's high desert for the most part. And then the particulate matter is blocking the sun and causing health problems and is actually serving to further suppress rainfall because it's not allowing the ground to heat up as much and overcome the hot air aloft. So it dampens the rain and increases the pollution. We see the same sort of thing with Saharan dust, which we get occasionally during the summertime. If you just threw it into some moist air, it might help make precipitation, but it's coming along with Saharan air, which is fairly dry, and so we get these murky days with lots of haze and not much relief in the way of cleansing thunderstorms.
Indeed. Like you said, it's complex and it's all interrelated. And thank you for sharing that with us. I want to go to Justin now. Justin, last week it was the first in our series on extreme weathers, and we looked at wildfires, droughts, and winds. And in that segment, we were consistently reminded that so much of weather is cyclical, that there's natural cycles and patterns and things like that. And with that affects wildfires as well. Would you talk to us about how the cyclical nature of weather affects storms, floods, hurricanes, and tornadoes?
Yeah, sure. Happy to do that. And before I do that, I just wanted to kind of add on to John's answer about this relationship between precipitation and kind of what the land surface can do to something like rainfall. A really good example that your listeners may know of is the Dust Bowl, which was this period of great drought in, the agricultural plains of the United States during, the 1920s and 30s. So one of the major factors, after the drought kind of started, there were human interactions on the landscape, right? How we planted the plains, removing grasses that had really long roots that hold soil to the earth. That was all removed. And so, you have really shallow rooting crops, which means that the topsoil can get mobilized more easily by the wind, picked up and carried by the wind. And once you have a drought, it's easy for the winds to pick up that soil, carry it up into the atmosphere, and then it makes it hard for sunlight to penetrate through that atmosphere and evaporate any moisture that would be at the surface, which could help generate clouds and create rainfall to kind of alleviate that drought. And so you have what's called this land-atmosphere feedback, where human management of the land under conditions of drought, actually led to further depressed rainfall because of the mobilization of all the soil, all this particulate, what we call aerosols, into the atmosphere. And it's similar to the role that our industrial aerosols played in the Atlantic, kind of accounting for this kind of multi-decadal variability that we see in the Atlantic Ocean. We also think that volcanoes sometimes have something to do with that, right? The volcanic eruptions emit a tremendous number of aerosols into the atmosphere, and that could block sunlight and decrease the amount of energy that gets to the surface, right? To the extent that something like precipitation, right, is constrained by energy, right? In order to rain, you need to have a source for that rainfall, and that source is the ocean, and you need to evaporate it, which means that you need energy to do that. And so you can think of precipitation as being energetically constrained. And in a warmer climate, right, like a really clear expectation we have is there's just going to be more energy in the climate system, and that just is going to mean that you're going to have increased moisture in general, and increased moisture is just going to drive increased intensity of all precipitation events, kind of, irrespective of atmospheric circulation changes.
Basically, you're saying that stuff in the atmosphere can actually block evaporation, like stuff
it can
like
block
dust.
The energy that you use that gets used for evaporation.
Okay, and that then minimizes rainfall.
Yeah, it can have a consequence for reducing, evaporation. What gets rained out has to be evaporated into the atmosphere, right? And you need evaporation as a source of supply. If we think about supply and demand from the atmospheric perspective, if you're an atmosphere, right, you source moisture via evaporation and you release it via rainfall. And so, yeah, your evaporation is constrained by the energy you have available to do that evaporation. That energy comes from the sun, right? And
particulate matter and stuff in between is blocking that energy.
Yeah, if you have a bunch of stuff scattering sunlight, less of it's going to get to the surface, and whether that's the land surface or the ocean surface, and it's going to reduce the radiation we have available for evaporation. That's a crucial land-atmosphere feedback under certain conditions.
And again, it helps connect the dots as to why this stuff happens and how it happens. But it also lets us know that I can understand now why you really are able to forecast a lot of this.
Yeah, I mean, on your question of kind of the cyclical nature of the climate system, right? Like, we have a really complicated Earth, right? We have land, we have ocean, we have atmosphere, we have the cryosphere, we have ice on land and in the ocean. And then we have kind of all the chemistry of all these things, right? and the biology of all these things. And these different systems operate on different timescales, right? The atmosphere is quite fast moving. The ocean is quite slow, has a lot of what we call thermal inertia, really high specific heat. It's easier, to warm up. It takes less energy to warm up a given volume of air by 1 degree than that same volume of ocean water, for example, right? And so it just means that these different components of the Earth system kind of deal with energy from the sun on very different time scales. And as they all interact, that can create oscillations in the climate system, kind of, periods of drought, and periods of extremely wet conditions, or warmer temperatures in the ocean for a set number of decades in the Atlantic, and then cooler ocean temperatures. El Nino, which is this kind of part of this wider phenomenon called El Nino Southern Oscillation, which is this relationship between ocean temperatures and the atmosphere in the tropical Pacific. Some of your listeners may know about how warm water kind of sloshes back and forth in the tropical Pacific, depending on a breakdown in prevailing winds in that region. And that can have huge consequences for the configuration of weather patterns we get around the world. Like if you just imagine you have a space heater in a small room, and that's a small space heater, right? That creates a very different experience of temperature in that room than if you were to have a radiator that took up the entire wall. And so that's the difference between having ocean temperatures that are really warm in a small geographic region versus being spread out over the entire tropical Pacific. It just creates very different energetics in the climate system. And these oscillations, they're a source of randomness to the extent that they're not well understood, right? But to the extent that we scientists can diagnose them and kind of understand them and say, for example, that multi-decadal variations in the Atlantic kind of temperatures are driven by stratospheric aerosols from volcanic eruptions versus being kind of innate oscillations in how, water from the surface gets carried down to depths and carried around the planet. To the extent that we can kind of name these things and characterize, the spatial scales over which they occur, the time scales over which they occur, and the consequences of them, they become a really powerful means to prediction, right, to seasonal scale forecast.
And is that how you all are able to predict at the beginning of the seasons about how many named hurricanes you'll have and things like that?
Yeah, I think a lot of that is rooted in questions of what the different what the tropical Pacific is doing in terms of its temperature and what the tropical Atlantic is doing in terms of its temperature.
When we come back, I want you to tell us the difference between, El Nino and El Niña?
La Nina, sure.
That one is the masculine and one is the feminine. We'll be right back on the other side with Justin Mankin from Dartmouth. And now we want to give a shout out to our sponsors. That is Natural Awakenings, Dallas-Fort Worth Metroplex Magazine, the Green, Healthy, and Sustainable Living Authority for the DFW Metroplex and North Texas communities. Print issues of Natural Awakenings can be found in all Whole Foods grocers, Natural Grocers, Central Market, Sunflower Shops, and many, many other locations, as well as available free for download online at nadallas.com. Check them out. Our other sponsor is North Haven Gardens, serving the Metroplex since 1951, the most respected horticultural establishment in North Texas, offering gardening and plant education, concierge services, DIY classes, gifts, and more. Check them out at nhg.com. And our other sponsor is Lynn Dental Care, practicing dentistry for over 38 years with a holistic approach, none mercury, looking at the whole body. Dr. Lynn is board certified by the International Academy of Oral Medicine and Toxicology. Check them out at lynndentalcare.com. Thank you, sponsors. Welcome Welcome back to Healthy Living, Healthy Planet Radio, to today's show in our series on extreme weather events. And today we are focusing in on hurricanes, tornadoes, storms, and floods. And we have with us today Dr. John Nielsen-Gammon, our state climatologist, and Dr. Justin Mankin at Dartmouth. And again, thank you all for making time to be with us today. Now, Justin, wanted to talk with you a little bit about tornadoes. Can you explain to our listeners, I guess maybe technically, what tornadoes really are and what causes them and what makes them an environmental event?
So, tornadoes are an extreme weather event that can emerge as a consequence of an extreme thunderstorm. And, like a tornado is characterized by a funnel of really rapidly moving air, kind of vertically oriented from the atmosphere to the land, picking up, any kind of debris on the land and moving it up into the atmosphere. So it's characterized by really, really, really high wind speeds, kind of owing to conservation of angular momentum. And the way they form, they're kind of, we know a lot about the kind of environmental or atmospheric ingredients that favor tornado formation. We also know a lot about the kind of geographic regions that are particularly well suited to have tornadoes form. Right?
Is that changing? In other words, are we seeing tornadoes?
The region, when we think about kind of the geography, we're really talking about kind of the physiography. So, kind of the location of things like mountains versus plains. A severe thunderstorm, as distinct from something like a tropical cyclone. A tropical cyclone needs warm ocean waters and needs to form just off the equator, for example, but not on the equator, right? And it needs a low wind shear environment. So those may be some kind of ingredients that you might need to kind of favor the formation of a tropical cyclone. And then if you have a weather disturbance and you have those ingredients, like maybe a hurricane forms. A severe thunderstorm, really requires, it requires moisture availability. But as distinct from like a regular afternoon thunderstorm that you might get, you need high wind shear. And the reason you need high wind shear is because it favors a particular structure of the storm, such that the storm is kind of siphoning up moisture and energy from one side of the storm and raining it out on the other, instead of trying to do both in the same location. So like an afternoon thunder shower, essentially kills itself because it rains over precisely where it's trying to evaporate moisture in. And that shuts off its source of energy. A severe thunderstorm has a configuration where its evaporation and kind of uptake of energy is in a different location than where it's tending to rain out. And that's because of this high wind shear environment that favors their formation, where winds, say, really high up are blowing in a different direction or at much greater speeds than winds closer to the surface. And so that kind of flattens out it creates this anvil type shape that you might associate with a severe thunderstorm, as distinct from just like an afternoon convective thunderstorm. Wind shear also seems to favor the formation of like rapidly rotating air. And so there are some indications, the precise mechanisms by which a tornado forms within a severe thunderstorm. We think that this high wind shear environment favors the rotation of the air. Like if you were to just imagine putting a ball on a flat surface, right? You could think of the surface itself as having really low wind shear. And if you kind of moved your hand over the top of the ball, right, that would be high wind shear aloft, and that gets the ball rotating. And the same thing is happening in the air. And then if you have a part of the storm where there's a massive updraft, meaning that the air is sucking up, air from down below, that could tilt this rotating air into the vertical. And that's how, there are some indications that's kind of how a tornado starts to form.
Indeed, it's complicated, but I imagine it would have to be for the damage it can cause. A couple of things, though, and I want to go back to What makes for a thunderstorm? I know it's thunder, but how does kind of describe that to us? What makes for a thunderstorm as opposed to just a very hard rain?
Yeah, well, I mean, a thunderstorm is kind of few different characteristics there. The first is that it tends to have lightning, right? The thunder is a consequence of, essentially when a lightning bolt strikes through the air, it superheats that column that it's traveling through to such a great degree that it creates this massive pressure differential, and that's kind of that pop you're hearing, right? It is this rapid expansion of air around where the lightning is taking place.
What causes the lightning? I'm sorry, what causes the lightning?
The lightning is caused by, there's a few different candidate processes. Within a thunderstorm, right? What characterizes a thunderstorm is how much moisture it has in it, and how tall it gets built. And if we're just kind of thinking about a thunderstorm, if it's traveling along and kind of sucking up moisture from the surface, evaporating it into it, as that moisture goes up into the atmosphere, it then cools and condenses, as John noted earlier, and kind of forms a cloud. But when it condenses, when water condenses, you can kind of think of water vapor as like a battery. Water is a form of energy on our planet. And so when you evaporate water, you've taken liquid water and you've added sunlight. And so that water is traveling up to high in the atmosphere, carrying that sunlight energy. And then when it condenses back into water, it releases that sunlight energy. And that's a phenomenon we call latent heat release. And that latent heat release actually warms the environment up where the cloud is, right? Making it more favorable to store more energy, because there is this fundamental relationship between warmer air having a greater moisture carrying capacity than cooler air. And so you have this kind of like nice feedback where, more evaporation, more condensation, more heat release favoring more evaporation and more water storage. And as the clouds build quite high, it's still very cold high up in the atmosphere, and you get a lot of ice formation within the clouds. You get a lot of hail formation within the clouds. And within the clouds, you're getting these different forms of water, right? Whether ice, liquid, or like semi-solid, super cooled water, all striking each other, hitting each other all the time. And you have a situation where you kind of have the cloud starting to organize itself by density. And then the striking of each other, they're shedding their electrical charges so that you have the cloud essentially turning into a big battery.
Indeed. And here in Texas, in North Texas, we get a lot of hail. You can drive up and down the street and see where it's been when you look at the dents in people's cars. And so the way I summarize what you're saying is that the hail, the lightning is all about energy up in the clouds as a result of the processes.
Yeah, so cloud microphysics and cloud processes, right, like the formation of hail and these ice particulates, they all bump into each other, and it kind of organizes the electrical charge of the cloud itself, and that tends to organize the electrical charge of the land surface, and then that electric potential builds to a point, and then, just like a cloud can only store so much water, this electrical potential can only, it gets to a threshold where you have a lightning bolt, and then you have the consequent thunder. The thing that's different about a thunderstorm versus a severe thunderstorm is really this wind shear factor.
And and really briefly, we only have 2 minutes to go, but really briefly, because I want to ask you something else before we go, what is wind shear? I remember it first coming to my attention, though, with a very devastating plane crash.
Yeah, so wind shear is just a measure that we use to assess how different wind speed and wind direction is at different levels in the atmosphere. So wind shear is really bad for the formation of a hurricane, because a hurricane likes to have a really nice vertical structure, right? Like it wants to look similar at the surface as it does high up in the atmosphere. But for a tornado, right, or a severe thunderstorm, wind shear is a really important ingredient. You want high degree of wind shear. You want wind speeds being much faster or in a very different direction, high up in the atmosphere than lower in the atmosphere, because that gets air rotating.
Last question, Justin, and I really appreciate you because you're really making us smarter. And this is the last question, and that is, we know climate change is upon us. What are we seeing, though, for the near future in terms of some of these extreme weather events like hurricane, tornadoes, storms, and floods as a result of climate change? And what is, I guess, the best thing that we as ordinary people can do to help drive solutions?
You know, given the frequency and magnitude of extreme climate events, what's pretty clear is you just need to open up the newspaper on any given day to see that we are, even here in the United States, very poorly adapted to the climate extremes we have right now. And these are climate extremes that we can actually identify the culpability of global warming on, right? These are things that have been made more intense or more frequent because of the warming we have already done to our planet. You know, and if we are poorly adapted to them now, that tells me that we're going to be poorly adapted to them tomorrow when they're going to be worse, right? The nature of the warming problem is that it's always worse tomorrow than it is today. And so I think, you know, the really important thing is for us to be thinking about mitigation and adaptation and investing in both of those very heavily to be resilient to climate extremes.
Indeed. Thank you, Justin, because that's what this conversation has been about, and that's what the purpose of Healthy Living, Healthy Planet Radio really is, to open up, unpack, and explain all of this to people so they can really see and know that to care and to take action is really not an option. And you all know so very much. This seems to be one area that we can really, really measure a lot. And then, therefore, if we can measure it, then we can project. And so we appreciate the work that you and others like you do. Thank you so much. We've been with Justin Mankin at Dartmouth and John Nielsen-Gammon at Texas Tech, our state climatologist. Thank you all. You have made us smarter today. And thank you, audience, for listening in today to Healthy Living, Healthy Planet Radio. The conversation starts here, but our goal is for it to continue in your home, in your social circles, your workplaces, at the water cooler, and in the grocery checkout line, so that we can all work together to realize that healthy living is simply not possible without a healthy planet. Our culture is a result of 1 trillion tiny acts taken by billions of people every day like yourselves. And each of these tiny acts can seem insignificant, but all of them add up, one way or the other, to the change that we each live through. This is your host, Bernice Butler. Thank you for joining us today, and please join us again next week as we talk more about extreme weather events, and you can listen to any of our past shows on podcast wherever you get yours. Thank you.